The integral formula is a little bit easier to remember for parameterized curves than it is for a curve defined by y equals as a function of x. A way to remember it is that if you have the distance, if you want to calculate the distance between 2 points, you figure out the change in the x-coordinate and you square it. You add it to the change of the y-coordinate, the square of the y-coordinate, and then you take the square root of the results. That's just the distance formula between 2 points. But if we want to get a correct, but if we want to do this, if we want to find the distance between, but if we want to find the arc length, what we're going to do is find the infinitesimal distance between infinitesimally close points and add all of them up. That describes an integral. Here we have the change in the y direction between consecutive infinitesimally close points. The dx dt is the change in the x direction. You square each of those, you sum them, you take the square root. Then you add up all of those infinitesimally distances, and the convergence, or the limit of that process, gives you the length or distance between the two. As long as the functions that define our parameterized curve are continuous, this will converge. It would tell us the distance from the first initial point to the terminal point. Let's take a look at an example. In this example, we want to measure the length of this particular path starting from time 0 to time 4. The arc length formula says that we have to take the derivatives of each of our directions. Then we substitute into the arc length integral formula. And to compute this integral, it looks like a trig substitution is a good idea because you have the square root of some sort of your variable squared plus another number here. That's a form for a trig substitution. Really, you want to use a trig identity to replace something like 25 plus 25 tangent squared with 25 secant squared theta. Because if you could do that, you can very clearly take the square root of the left side or the right side of this equation and then just hopefully have a trig integral that you can solve. Well, if you want a 25 tangent squared theta here, you probably should replace your t with a 5/6 tangent theta. If you do that and you square this expression, this 6 in the denominator becomes a 36, which cancels out with this 6 in the numerator. This 5 in the numerator becomes a 25, which matches perfectly for that substitution. But if you're going to take the to do the substitution, you have to find the appropriate differential substitution. So you take the derivative on the left side, and that gives you your dt. You take the derivative on the right side, that gives you your dt. You take the derivative on the left, and that gives you your 5/6 secant squared theta times d theta. With the appropriate substitutions, our integral looks like this now. And we use that trig identity over here so that we can replace this sum of squares with a 25 secant squared theta. Applying the square root to the 25, that becomes a 5, to the secant squared, that just becomes a secant. And now we hope to integrate secant cubed theta. So we use the reduction of order formula for the secant, which has power cubed, so you can reduce the order. It looks like this. This last integral would be one of the fundamental integrals. We get the following integral over here. And it looks awfully complicated. And to complicate things further is that we need the integral in terms of t and not theta, which means we have to convert back from this theta relationship back into t. To take this equation and rewrite it as a ratio, so you can use the right triangle rule to convert. That is, you have t theta you have tangent theta equals 6t over 5. Using the right triangle definition of tangent, the numerator of the fraction is the side opposite of the angle, and the denominator is the side adjacent. Because it's a right triangle, we can find the hypotenuse by taking the sum of squares and taking the square root. Now, if I want to convert secant theta into terms of t, I remember that secant is the hypotenuse over the side adjacent. And I already defined tangent as this ratio over here. We eventually get this particular integral, and now we can substitute in our limits of integration from 0 to 4. Notice I avoided substituting the limits in the form above because I didn't bother figuring out what the angle was for the values of t, 0 or 4.